Right, today what I'm going to do, I want to discuss with you, I think, one last type of derivative, which I don't think we discussed it explicitly. Then after that, we're going to look at what we call logarithmic differentiation and see how that simplifies differentiation somehow. So, first of all, let's look at this. Now, first of all, let's recall how we use the implicit differentiation to derive some derivatives. For example, I think after learning implicit differentiation, we discussed this kind of derivative, like a to the power f of x. F of x, there is any function, could be x squared, sine, any trigonometric function, any other function there. So we said, what we did actually, we said we could derive a standard derivative of this type of function by applying ln, on both sides. Then we applied ln, this is what we got. Ln equals to ln a f of x, Then applying properties of ln, we got that to be f of x multiplied by ln of a. And then during that, we need not to lose sight of the fact that what we're actually searching for is dy dx, and at that moment we did not know how exactly to get to this dy dx. Then this is the strategy we applied that, knowing the implicit differentiation. So now, having ln of y, knowing the derivative of ln and knowing implicit differentiation, ln of y equals to ln of a multiplied by f of x. Please guys, note that ln of a here is a constant. It could be 2, could be 3, a number, is that right? So now, if we're going to differentiate these both sides, let's say we differentiate this expression, both sides with respect to x, what we're going to get here? We get the derivative of a ln, the usual way we get it. It is 1 over the argument multiplied by the derivative of the argument. Then that will be equals to, remember I'm differentiating both sides, then that will be equals to ln, the constant, ln of a, the constant multiplying the derivative of f of x. Now, remember, we're looking for dy dx. So now we've got an equation which involves dy dx. The only thing left for us is to make this dy dx up to the formula. Is it? So first of all, let's multiply both sides by y. Is it? Multiply both sides by y. So we are going to get dy dx equals to ln a multiplied by f prime, that is the derivative of the argument of the function we're given here, multiplied by y. But we know y from the beginning, is it? We know y. What is y? Y is that function we're given. So which means at the end of the day, the derivative of that y is y f of x, substituting this y, multiplied by f of x prime multiplied by ln of the base. That is prime there. That's what we discussed. We got that. There's no problem with that. So what I wanted to why I'm recalling this for you is because today I want to discuss, let me see. Today I want to discuss this situation with you. Now, remember, if you've got y equals to a, f of x. There's no way we can avoid thinking about log base a of f of x, because those functions are related to each other, isn't it? It doesn't make sense to look at the derivative of this and just ignore that. Is that right? Okay. So, what are we going to do here? Right. The strategy I think we can adopt here is to apply, not really apply lin, but change of base. Notice that this changing base, I can say this is lin f of x over lin of a. Just check your formula for change of base. You are changing from base a to base e. This is how we should do it. How together? Okay. Now, if that is the case, then which means this is actually our y. Now, if I want to differentiate y, you must notice that what we have here, you have got y equals to 1 over ln a multiplied by ln of f of x. Maybe normal there, let's put our absolute value bracket there. That is important. Now, to differentiate this, we can actually go back to what we saw here. We're differentiating a linear. What did you do? 1 over the argument multiplied by the derivative of the argument, is it? Yeah. So then, coming here, to differentiate this, we can now say dy dx equals to, this is a constant, this is the function of differentiating. We'll say now 1 over the argument multiplied by derivative of the argument multiplied by this number 1 over ln of the base of the function given there. Does that make sense? I mean, the argument logical from the beginning to there. Does it make sense? So then, at the end here, what do you have? You have a derivative of a logarithmic function. Sorry, I was looking at that side. I was looking at this side. This is the function of differentiating. This is the derivative of this function. So this is the base of that logarithm. Now look at what this is saying. It's saying the derivative of a logarithmic function is 1 over the argument multiplied by the derivative of argument multiplied by 1 over the ln of the base. If you look at what is happening here compared to what is happening there, here we're differentiating an exponential function. Look, the exponential function, exactly as it is, multiplied by the derivative argument multiplied by the ln of the base, which means what we do with the ln of the base in differentiation of the exponential, we multiply. But when we go to the differentiation of the logarithmic function, we actually divide. Is that clear? I'm just trying to highlight that so that don't forget these things very, very easily. That's how they are related. In exponential, you multiply by ln of the base. In the logarithmic here, you divide by ln of the base. But when base is e, this does not show. Why? Because this would be 1 over 1, then you don't even write it. But any other base, this is important, you've got to write it. How together, guys? Any question there? Then, if that is the case, then let's let people do an example, at least one example. Say example. Let's say we've got y equals to log base 5 of cosine of x. Can you play around with that? I'll give you some few minutes or few seconds to play around that and then suggest what I should write here as a solution to this. Right, let's see who is ready to give me a suggestion. What should I write as a solution to this? I'll write here dy dx. What I say? She suggests that I must write 1 over ln 5, which you can just call ln of the base, multiplied by 1 over cosine x, multiplied by, let's first of all write this so for to guide people, multiplied by the derivative of cosine x, so people can see what has happened, isn't it? 1 over ln of the base multiplied by 1 over the argument multiplied by the derivative of the argument. All together. Then we can simplify according to what she's saying. She says we must write 1 over ln 5 multiplied by 1 over cosine of x multiplied by this derivative. So here we must differentiate. This is the only spot we must differentiate for that point. So we must differentiate correctly for the whole derivative to be correct. So that is what? Negative sine x. Then we can simplify that. I think that would be what? That would be 1. Sine over cos is tan, isn't it? So we've got a minus sign there, which is minus tan. So at the end of the day, we've got minus 1 over ln 5 multiplied by tan of x. All together. So now what is left for you is to go and sort of do this again and again, twice and twice. You remember the story of twice and twice, isn't it? Yeah. So otherwise, this thing does not make sense. Now, I'm actually setting a trap here, and this trap I'm setting as a kind of motivation to show even our heroes in differentiation that there's still something to learn. Guys, let's say I give you a function like this. Pi to the power x. Then I give you x to the power x. Then I give you y equals to x squared plus x multiplied by e to the power x squared multiplied by tan squared x multiplied by 5 to the power sine of x. Divided by 16 to the power x squared plus 2x. All right. I want comments. I'm inviting comments. Are you fine here? Why are you fine there? Is it what? It's a simple exponential function base 8. Is that right? Are you fine here? What about here? Y equals to x power pi. Are you fine here? Are you fine here? Are you fine there? Are you fine there? What are you going to use here? Who can tell me? One person raise up your hand and tell me what they're going to use here. Come again? You are saying power rule. Yes, I agree with you. This, when you differentiate this, it will be just pi x pi minus 1. What about here? Why don't you apply this same rule? You said you're not comfortable, really? Did you say you're comfortable with this one? Here, are you comfortable? No, good. It's good that you're not comfortable. This takes you to another discussion which we call logarithmic differentiation. Even this situation here, let me tell you something here. I don't want to sound a bit derogative, no? But I'll try to sound mildly derogative. If somebody thinks of applying a quotient rule here, then apply product rule in the numerator there, then you must be mildly crazy. You must be mildly crazy. Let's set ground rules here. Let's set ground rules here. This looks like a power function, yes or no? Let's put one ground rule there. Power rule is for sometimes I get, what are you comfortable with? Are you comfortable with calling this an exponent or a power? This, like here, pi x, what are you calling x there? Are you saying x is a power of pi, or you're saying the exponent of pi? It's the power of pi, is it? Okay. So then, let's say this x is a power of pi. So this x here is the power of this x, isn't it? Okay. So let's say power rule is defined for powers which are numbers. Not functions. That is, in other words here, even if it has got a structure of a power function, that power rule is not defined for powers which are functions. It's only defined for powers which are numbers. In other words, this x, if it was a 2 or a 3 or 4, explicitly looking like a 2, looking like a 1, looking like a 4, looking like a pi, then I would apply power rule altogether. So power rule is defined for that. Then 2, product rule. Is for two vectors I haven't discussed product rule for 3 functions. We haven't done that. So I would advise you at this stage, restrict the product rule to when you are dealing with 2 functions multiplying each other. This is what I'm talking about here. The vectors are functions, isn't it? F times G, U times V. Restrict product rule to that. Don't go beyond that. All together? Okay. Then also, product rule here, I can also say, or take my division sign there, or quotient rule. It's also for 2 vectors. I can take them with vectors. F over G is F over G multiplied by 1 over G. Not F over G times G over X, F times H over G, or F over G times something else, only two factors altogether. So once you understand that very well, then where we're going, you are safe. Let's start with this one, logarithmic differentiation. We start, that thing gives us a kind of a power structure. The skeleton is the same like that one of a power function, but it's not the same thing, because this is a function elevating another function. I could have also written here x power sine of x squared. Now, how do we tackle this? We have implicit differentiation, we know that. Then what we do is we apply ln on both sides here. Then we apply the properties of ln. Then what do we have? We have got a product rule situation here. We've got two functions. We've got an implicit situation there. And we know here we are looking for dy dx. Are we together, guys? Are we together? So now look at how ln has helped us to kind of, ln plus the implicit differentiation has helped us to handle this. So now let's differentiate here. The chorus. Somebody called it the chorus yesterday. 1 over the argument multiplied by the derivative of the argument. Differentiate here, product rule. X times ln 1. So differentiate x first, we get 1. We multiply by the second function without differentiating, plus we differentiate the second function, multiply by the first one without differentiating. So again 1 over that argument, multiply by the derivative argument, dx is 1, leaves like that. Then what do we have next? We've got ln x plus 1. But now we've got an equation which has what? Dy dx. So let's solve for dy dx. Solving for dy dx, in this case, it just demands multiplying by y on both sides. Then we'll give you a ln x plus 1 brackets multiplied by y. If you want, you can sometimes leave the function like that, especially if this y is very like cumbersome. Something cumbersome. According to my understanding of the word, I've never seen the word cumbersome in the dictionary, but according to my understanding of the word cumbersome, it's something like this. If y was something like this, I would write it there. You understand what I'm saying? I won't write it there. I will just leave my answer as ln x plus 1 multiplied by y, and assume that the examiner knows y, or the marker knows y. Are we together? But if it's a simple y, like more or less like this one, which is more or less like easy to handle, easy to look at, not cumbersome, I can write this thing now like this. Or I can just write it as ln x plus what? 1 multiplied by x to the power x. Are we together, guys? Is everybody comfortable with that? Okay. Questions? Can I listen to questions, comments? Now, this type of simplification of differentiation, or this type of application of the logarithm function to differentiate, is what we call logarithmic differentiation. Are we together? Now, what is it targeted for? I've said it here. For products which involve more than 2 factors. For quotients which involve more than 2 factors in numerator, or more than 2 factors where in denominator. Otherwise, quotient rule is just for f over g, 2. Product rule, f times g, only 2. Once it exceeds that, then we appeal to the logarithmic differentiation. Let's tackle this one now. This one. Now, let's try to look at this ugly expression and see how we... Actually, I wanted to frustrate you with this thing. I had it, when I was writing this thing, I could see people getting frustrated. Saying, now, what is this? So, but that is a kind of motivation. Sometimes it's good to shock people. When they wake up in the shock, they learn something. That is always interesting to do it like that sometimes. Not always, but sometimes. Now, having an expression like this, guys, please. Having an expression like this, I don't want to see anybody attempting to do quotient rule or product rule. Because what is this going to do? If you're going to differentiate this numerator, you've got to do product rule with 1, 2, 3, 4 functions. Product rule only on that part of the numerator. Then multiply by this. It's already, before you do it, when you think of quotient rule, already it looks clumsy, it feels clumsy. I mean, feel it. I mean, it is here, you can see it. It feels clumsy to me. So please avoid that. Once you exceed 2 functions in a quotient or in a product, avoid that. If I see you attempting to do it, I'll stop marking and just say, this guy never attended my class, so how can you examine somebody who never attended your class? It's not good. Now, let's go on with this. We apply lean on both sides. That's the strategy. Then, obviously, it will be lean of this quotient. I'm not going to apply lean to all such a big thing. I will immediately apply the properties of lean, isn't it? So, this will be lean of the numerator as x squared plus x brackets. Please, people, use brackets. There are people who sometimes ignore using brackets and the things look very, very meaningless. That's lean of the numerator. According to the properties of lean, I will say minus lean of 16 to the power x squared plus 2x. It is clear that that whole quadratic expression there is a power of 16. But when I start applying the properties of lean, both sides here and there, I think I must use brackets around that. Altogether. Otherwise, it's going to have a different meaning altogether. So now, let's start by applying this. This is m times n times l times p. So a lean of a product is the sum of the lean. So I'm going to get here lean x squared plus x plus lean of x squared, lean of e, x squared, lean of e, x squared, plus lean of tan squared, plus lean of 5 sine x minus brackets. Please use brackets there. If you don't use brackets, that expression is going to have a different meaning altogether from what you started with. It will be just 2x multiplying that, which is not correct. Now listen. Up to here, I haven't done any differentiation. So strategies, you apply your lean and simplify all relevant properties of lean, which you can simplify before you start differentiation. So now here, There's no property I'm going to simplify here. I'm just going to have this as ln x squared plus x, and that in brackets. Here there's a property I can apply, that power property. This can come this as x squared times ln e. But ln e is what? 1. So there I'll end up with x squared. Is that clear to everybody? Okay. When I come here, there's no property I can apply here. There's no property I can apply. I'll leave it as it is. Then I have plus ln tan squared x. When I come here, I can put, there's a power, sin x as a power, I can put it here and have sine ln of 5. Then I'll write this thing as ln 5 brackets that number sine of x, just to write it as a coefficient nicely. Try it at home. Try it at home. Just tell me tomorrow when you come what it gives you. Okay. For now, let's use this way. Right, minus x squared plus 2x ln. Right. I'm not discouraging you to try, my friend. Try and see what are the disadvantages of that and advantages of that. Then if the advantages, share them with us. If there are disadvantages, maybe you can advise your friends whichever way you want to. Is that right? Yeah, try it. Right. Listen, guys. Up to here, we've finished. There's no other property of ln we can apply. So look what I'm doing there. I'm going to draw a red line. And emphasize that if you're doing ln differentiation, first of all, apply ln, simplify all the properties of ln as far as possible. As far as is possible. Then you can start differentiating. So what I'm going to do now, after this red line here, I'm going to start differentiating. What am I searching for? I'm searching for dy dx. That's what I'm looking for. At the end of all the calculations I'm going to do here, I must deliver dy dx. Is that clear to everybody? Okay, here it's going to be 1 over the argument multiplied by dy dx. I think you can see where I'm going to apply the chorus, where I'm not going to apply it. It's up to you. When I come here, I'll just say 1 over x squared plus x multiplied by the derivative of the argument, which is going to be 2x plus 1. I'm doing it a bit fast there. I'm supposed to let everybody understand what's going to happen, isn't it? Yeah. It will be 1 over x squared plus x multiplied by 2x as a derivative argument over 1. Then I multiply the two fractions, I get something like that. When I come there, I'll have my usual power rule. When I come here, I do exactly the same thing. Plus 1 over the argument, which is tan x squared, tan squared x, sorry, multiplied by the derivative of tan. There is a power function. Power acting on tan. So I'll have 2 brackets tan x to the power 2 minus 1. That's my power differentiation applied on tan, multiplied by the argument of, the derivative of the argument of the power 2, which is, the argument is tan, so the derivative is, who remembers the derivative of tan? Good, sec squared x. Then I'm done there. Then when I come here, I just have a number multiplying sine. So the derivative of sine is, so that number will multiply the derivative of that function, so it will be ln 5 cos x minus, here I've got ln 16 multiplying this function. So when I come there, I just differentiate the function and the constant will multiply the derivative. So what's the derivative there? 2x plus 2. Applying our power rule there, then that's the linear function. The derivative is 2. So okay? 2. Any questions that far? Any questions that far? Okay? Yes? Come again? Here. Why am I not using product rule? I've got one function sign here which I can see. I'm asking you, which other function can you see there? No, is it a function for you? What is this argument? What is this argument? That's question 1. What is it in the independent variable? Question number 2. What's the independent variable? Here it's sign. The independent variable is x. And the function which was given, y, it was shown clearly dependent on x. Now your ln function you are talking about now, what is its argument? What is its independent variable? Can you answer those questions? Ask your neighbor there, please. Are you getting an answer? Are you getting an answer? What does he say? There's no argument. Ln is acting on 5. And the 5 is not a variable like x, so you cannot consider the function. It's actually constant. Put it on a calculator there. You will see the number. It will be a decimal number. Is it really necessary to put it on a calculator? No, it's not. Let's go. Let's move. Let's move. Let's move. So dy dx. Sorry, just hold on. Dy dx will be equals to. So we're saying dy dx will now end up multiplying both sides by y here. We'll end up writing a y brackets. Please guys, I think you will accept my apology. I'm really lazy to write all this thing inside here, isn't it? But everybody must try to imagine that this thing, actually you have to write it because you've got to feel it so that you get used to it. You write it inside there. All together. So I'll cheat that way there. I'm not going to teach that one, but I'm going to cheat and everybody assume that I've written that thing inside there. All together, guys? Yeah. That is linear differentiation. So now, I think there's no product of functions which you cannot differentiate. There's no quotient of functions which you cannot differentiate, thanks to logarithmic differentiation and implicit differentiation. Thank you for listening. As usual, it's Charles Sugar's fun.